What is
Light!
Baby, don't hurt me no more.
Light is a transverse electromagnetic wave that's produced by vibrating charged particles. Here we see this electron here, and when it vibrates, it produces an electromagnetic wave, such that we have magnetic field lines in red vibrating perpendicular to electric field lines in blue. This electromagnetic wave propagates at the speed of light, or c, known as the cosmic speed limit, where the speed of light is 3 times 10 to the 8th meters per second, or 186,000 miles per second. These electromagnetic waves are not mechanical as the waves we talked about before, such as water waves and sound waves. That is, they do not require a medium. Evidence for this is when we look at stars in the night sky. We can see their light even though they're very far away. As they produce an electromagnetic wave, this wave travels through space to our eye here on Earth without much material in between us and the star. So we know about visible light waves, but what are the different types of light waves? Let's see. The electromagnetic spectrum. Here we see light waves are transverse waves. We can see the visible part of the electromagnetic spectrum, but that's only a very small part of the entire spectrum. There are also radio waves, microwaves, infrared, ultraviolet, X-ray, and gamma rays. We can distinguish between the different types of light waves by looking at their frequencies and wavelengths. Here we can observe that the radio waves actually have the lowest frequency. There aren't many per second, but when we work our way up to gamma rays, we have many waves per second. That is, gamma rays are the highest frequency light waves, and radio waves are the lowest frequency light waves. We can also observe that radio waves have the longest wavelength, that distance from crest to crest, whereas the gamma rays have the shortest wavelength from crest to crest. Now the size of these wavelengths of radio waves are on the order of buildings, or several kilometers, that is 1,000 meters, whereas gamma rays can have a wavelength on the order of atomic nuclei size, or 10 to the minus 12 meters. It's also important to note that objects that produce these different light waves vary in temperature. That is, a very low energy cool object emits radio waves, but a very high energy object, high temperature, will produce gamma rays. Let's take a look at how objects appear at different wavelengths. So how do objects look at different wavelengths? Well, here we have Alex here on the left with her ugly sweater. What frequency of light enables us to see her ugly sweater? Well, here we can see her ugly sweater due to visible light rays reflecting off her sweater into our eye. What about this picture here in the middle? Well, this is looking at your hand with X-rays. Here, X-rays will go through your hand, but not through the bones, enabling us to see the bones. Here's a picture of a dog on the right. What frequency of light do you think this picture was taken with? Well, this is an infrared picture. Infrared shows us different temperatures or heat emitted by objects. Here you can see the highest intensity infrared rays would be the eyes and mouth and ears of the dog, and the lowest intensity infrared rays, or lowest temperature, would be the nose of the dog. Here's a picture of an object in the solar system that's visible in the night sky, but taken at a wavelength you're not familiar with looking at. Can you guess what object this is? This object is the planet Jupiter, more commonly to you in terms of visible light. So what type of wavelength are we looking at here? Here we can see the planet Jupiter, but what are these two dots here to the left and right? Well, when we look at Jupiter in radio waves, which are a type of light wave, we can see these two objects here, or solar wind particles trapped in Jupiter's magnetic fields. Those features are not visible in visible light rays from Jupiter. So by looking at objects at different wavelengths, we can learn more about them. Multi-wavelength astronomy. Astronomers observe objects at different wavelengths to learn more about them. Here we have a picture of the Crab Nebula. This is the Crab Nebula in the optical wavelengths. And the Crab Nebula is located about 6,500 light years away in the constellation of Taurus the Bull. In 1054, a star went supernova and produced this nebula, which is about 11 light years across. Now in optical we can see it this way, but if we look at it in radio waves it looks a little bit different, and same thing in infrared. And especially if we look at the Crab Nebula in X-rays, we see this more disc-like feature and a brighter spot in the middle. This is actually evidence of a pulsar rapidly spinning, which is the leftover core of the star that exploded. So as you can see, we can learn more about astronomical objects by looking at pictures taken of different wavelengths. This infrared picture was taken by the Spitzer satellite, which is in orbit around the Earth, the Chandra X-ray satellite, which is also in orbit farther out from the Earth, the Hubble Space Telescope, which looks at optical, and radio telescopes on the ground that look at those radio waves. Each picture can tell us something different about the object, and thus observing an object at different wavelengths can give us a better understanding of the object itself. The spectra of light. In 1704, Newton did research not only with his three laws, but also in optics. He discovered the phenomena called dispersion, which is the separation of white light into its spectrum of colors, or Roy-G Biv. This type of spectrum is called a continuous spectrum, whereas we just take the white light through a prism and we observe it and we see the full spectra of colors: red, orange, yellow, green, blue, indigo, violet. There are also two other types: an emission spectrum, which is produced by a gas, and an absorption spectrum that is produced when a gas absorbs lines from a continuous spectrum. Let's take a look at these two spectra a little more closely. Emission spectra are produced by a gas, and those appear as bright lines. These emission spectra are considered to be the fingerprints of the elements from the periodic table. Here we can see the emission lines of hydrogen. You can see there's 1, 2, 3, 4, 5 lines at these distinct locations. No other element has 5 lines at those exact locations, which is why the emission spectra is kind of a fingerprint for that element. Helium has lines at these locations, neon, sodium, and mercury, etc. No two elements have the same number of lines at the same exact locations. An absorption spectra is something produced by a gas absorbing parts of the continuous spectra. These appear as dark lines and reveal the chemical composition of the object. Astronomers do this to figure out what stars are made of. Here we can see a little picture of our sun, and as the light goes from the interior of the sun to us on Earth, the different elements in the sun's layers can absorb different frequencies or wavelengths of light. Here we have a picture of the sun's absorption spectrum, and you can see these different letters, especially C, which is a hydrogen line, D1 and D2, which are sodium lines, and some other lines here. We can actually look and see which lines are missing will tell us what elements make up the different layers of the sun. This is how we can understand what the sun and other stars are made of, and not having to travel the millions of miles or light years to them. Thank you for watching, and see you in class.